We are continuing with the concept of logic minimization and utilization of Boolean algebra and Carnot maps for looking at the circuits more deeply, optimizing it, and so forth. But now what we're going to be doing is we're still going to be utilizing Carnot maps. So you're still going to be looking at logic and Boolean expressions and all that. But then this time, not necessarily for the purpose of minimizing a circuit, but then for timing analysis of it. And also correcting if there are timing hazards, which I'm going to be defining in a few minutes. So let's get started with that. We are looking at timing hazards. What is a hazard? Here is a circuit that a very simple circuit, two AND gates, one OR gate, and then remember before I just draw a circuit. Now I'm putting some delays in the circuit. Let's say 7 nanoseconds for the AND gate, 3 nanoseconds for the OR gate, 7 nanoseconds for the lower AND gate, and the inverter is 5 nanoseconds. Why do I choose these values? Well, let's not worry about this. I want to show you something that happens in this circuit considering these delay values here. Let's say my ABC begins with 000. I'm sorry, 111. My ABC is 111, and therefore B is selecting either A or C, and therefore my output is initially 1. So you're seeing a 1 here, a 1 here, a 1 here. My output is 1. Okay? Logically, if my B changes to 0, that means this stays a 1, this stays a 0, C stays a 1. Logically, what happens? Well, logically, if B is 1, it's selecting A, which is a 1 to the output. And if B is 0, it's selecting C, which is also a 1 to the output. And therefore, logically, Y is 1. Okay? So I shouldn't worry about anything, right? B changes from 1 to 0, and then my output is 1. If B changes back to 1, then my output is still a 1. But considering these delays, let's see what really happens. At one point, B changes from 1 to 0. So I still have a 1 here. Now this changed to 0. And my C again remains a 1. Let's look at the signals in the middle. I have a W, which when I have a W, which when A and B were 1, this was a 1, X was a 0, okay? And therefore, my W was a 1 here, my X was a 0 here. Now that my B is changing to 0, what happens is my W changes to 0. But then, because B complement changes to 1, therefore this changes to 1. Okay? And eventually 0 and 1 or together for the gate for the output gate, therefore the output should remain 1. But then what really happens is not exactly that. So let me also put the output of the inverter here. It was a 0 and now is a 1. Okay. Now is a 1. V. Okay. 5 nanoseconds after B changes to 0, the inverter output changes to 1. Okay? Now, I said logically, when B changes to 0, V changes to 1. But then if you consider the time delays, that doesn't happen immediately. It takes 5 nanoseconds for V to become 1. Okay, fine. At the same time, what is happening, when B becomes 0, 7 nanoseconds after that, W becomes 0. So when B becomes 0, 7 nanoseconds after that, W becomes 0. Okay? But then something else starts happening when the input V of the lower AND gate becomes 1. Okay? Not only that, something else starts happening also at the same time. So two pending things happen. So see, this and this happened started happening at the same time because their input changed at the same time. But then W became 0 after W became 0 after 7 nanoseconds. The inverter output became 1 after 5 nanoseconds. Okay? The initiation was exactly at the same time. That's when B changed to 0. Now, my output gate at time 7 sees something is changing. My AND gate at time 5 sees something is changing. Okay, so at time 5, the lower AND gate sees a 1. It also had a 1, and therefore it's quite happy. It says both my inputs are 1, so my output has to become 1. Okay, that happens after 7 nanoseconds. Now, that 7 nanoseconds adds up to the 5 for the input change, and therefore 12 nanoseconds after B changes to 0, my X output changes to 1. But then remember, I said something else is happening also. And that is at time 7, the OR gate output sees a 0. At time 7, the OR gate output sees a 0. How about its input? It's the OR gate input. The upper OR gate input sees a 0. The lower OR gate input, what does that see? That sees still a 0. The OR gate that sees a 0 on its upper input, and the lower input is also a 0, what happens to it is 3 nanoseconds after W changes, that means 10 nanoseconds altogether after B changes to 0, 10 nanoseconds after that, my Y output, okay, changes to 0. This is 10. A 7 plus a 3 becomes a 0. But then, now these times are all relative to the time that B changes. Okay? It's all relative to the time that B changes. At time 10, my output Y changes to 0. But then only 2 nanoseconds later, the lower input becomes 1. 2 nanoseconds later, the lower input becomes 1, and therefore 3 nanoseconds after that, my output changes its mind, and at time 2 nanoseconds later, and then 3 nanoseconds later, that means 5 nanoseconds after that, my output changes back to 1. Okay? 5 nanoseconds after that, that means 10 plus 5. So if I want to be writing these relative to B changing from 1 to 0, that's 15. That's really not a good way of saying it. I think it would be better to say plus 5. That means 10 plus 5, it becomes 1 again. All right? I guess to be accurate, we put 15 here. So what do I have? My output that was supposed to stay at 1 when B changes from 1 to 0. Logically, it should have stayed 1. As you see, the final value is still a 1. But then it has a glitch. It has a little period of time that the output is wrongfully 0. Logically, wrongfully 0. That's called a hazard. What kind of hazard is it? This is a one hazard. Why one hazard? Because the output was supposed to say 1, but then it is not 1, it is 0, it is one hazard. If my circuit was notice that this is an AND OR circuit. This is a sum of product circuit. If it was a product of some circuit, I would have a 0 hazard, means the output would be 0, and then I would get a 1 that would be the wrong value. Nevertheless, that's not the issue. The more important issue here is that I have a hazard because of B changing from 1 to 0. If I continue doing this, does this happen again? Let's do that. Let's continue doing this. And this time, here, my B changes from 0 to 1. 0 to 1. My B changes from 0 to 1. 0 to 1. Okay? 5 nanoseconds after B changes from 0 to 1, V changes to 0. V changing to 0, 12 nanoseconds after that, this one changes to 0. B changing to 1, the upper AND gate has 2 1s, and therefore 7 nanoseconds later, this changes to 1. Now look at my OR gate inputs. The OR gate input, the upper one was 0. This was 12. Okay? The upper one was 0. The lower one is 1. 7 nanoseconds later, W becomes 1. 7 nanoseconds later, W becomes 1 here. And then my output is seeing both W and X being 1 for a short period of time simultaneously. And therefore, not only my output is not left down to 0, but also both inputs are 1 at one point. So what is really happening in the first case, when B changes from 1 to 0, there will be a little time, which is the 5 nanosecond time, that the lower input of the OR gate wants to become 1, but it has a delay. The upper input has already became 0, and therefore my output will be left with 2 zeros on its inputs. Okay, 2 zeros for a short period of time. It will be left with no 1s on the input, and therefore the OR output drops down to 0, but then it comes back up. In the second case, the green case I'm showing, because of the delay, there will be a time period that both my W output of the AND, or let's call it the input of the OR, the W input of the OR and the X input of the OR, both of them are on, both of them are 1 at the same time. And therefore, what hazard happened at in the previous case, in the first case, it doesn't really happen in the second case. Actually, my output is reinforced with 2 1s for a short period of time. It's not left out in the cold. In the first case, it's left out in the cold, and therefore a hazard happens. Okay? Well, what is this hazard? So here I have this situation. that leaves my output out in the cold. Let me show you this situation. No, let's do this. This situation, for this period of time, both inputs of the output are 0, but then here, for the same exact amount of time, which is 5 nanoseconds, both of them are 1. Okay, the first case is a hazard. The second case, no, it's even a reinforcement of the output of the OR gate. So here is 0, 0. This is 0, 0. And this is 1, 1. Okay? I had to do this analysis only considering the timing. The problem is I wouldn't be able to get this information from my Carnot maps, okay, or from just logical look at the circuit. I can look at the circuit and by analyzing the path and the delays and all that, I could, instead of doing all these little detailed timings, I could look at the propagations and be able to come up with this output timing. Let's do this. See, B has a path to output. It also has a path to the output. These two paths are complementary. Okay, these two paths are complementary. That means either the lower path is active or the upper path is active. The lower path has altogether a 5 nanosecond, a 7 nanosecond, a 3 nanosecond, 15 nanosecond delay. The upper path has 7 and 3, 10 nanosecond delay. Okay? If B changes so that the shorter delay path is switching to the longer delay path, okay? The shorter delay path is switching to the longer delay path, it means that the shorter delay path will go through the longer delay path, hasn't gone through yet. And therefore you get a glitch. Therefore you get a hazard. Okay? Shorter delay path is when B is 1. Longer delay path in this case, because of the inverter, is B is 0. Okay? The shorter delay path that makes the output 1, and the longer delay path that makes the output 1. When you're switching from one to the other one, if the shorter delay path, you're switching to the longer delay path, you get a hazard. When you're changing from longer delay path to the shorter delay path, no, you don't get the hazard. Okay? That's all very good. But then the problem is, how could I get this information from the Carnot map? The upper gate is AB, is this one. The lower gate is BC, which is this one. Actually, I have the blue map. The blue map. Or the pink map. BC. Okay. And then this one is AB. Okay. They go into the output OR gate. Half of it from there. The other half of it from here. Okay. All right. Can we see what we said there on this cardinal map? Look, we said that if I have a gate that is leaving its output, is zeroing its output, and the other gate hasn't been able to make the output 1 yet, and there is a gap between these two, then that's a hazard. Okay, let's not worry about the delays yet. If I'm going from map blue to map pink, I'm getting a hazard. What it means is, instead of doing the circuit like this and doing the timing like this, all I can do is look at the cardinal map and say, if I have two adjacent ones that are not covered by the same map, that means these two are not covered, then I have a potential hazard. I have a potential hazard. I didn't say I have necessarily a hazard. I say a potential hazard because that doesn't tell me anything about the timing. Okay? So what I say is, because of these two adjacent ones that are not mapped together, I can tell that ABC 110 changing to 111, changing to 111, ABC 111 changing to 101, or the other way around, I have a hazard. Which way? I don't know. Because all I'm reading now is reading from the cardinal map. If I'm reading only from the cardinal map, this is all I can tell. That the two adjacent ones that are not mapped together, I'm going to get the hazard. If you want to do the timing, then that's a different story. Okay? If you want to do the timing, you do this. You say the blue map, okay, corresponding to this, is 7. This is 7. This is 5. And this is 3. So this is potential hazard. Okay. Now, in order to find if these hazards really happen or not, I have to look at the duration of each path. The upper path, or the blue path, is 7 plus 3, that's 10. Okay? The red path is 7 plus 3 plus 5 is 15. Then I say, when I'm changing from the shorter path to the longer path, well, shorter path means ABC 1, 1, 1. Okay, ABC 1, 1, 1. That means from this one, I'm changing to the longer one, which is 101. That means if B changes from 1 to 0, I'm going to get a hazard. See, I didn't really go back and look at the circuit. I'm only reading it from the cardinal map because I calculate the delay of this, of the blue map. The delay of the blue map is 10. The delay of the red map is 15. And then changing from the 1 from 10 to 15, that's when I get a hazard. When you are not specifying the timing, when you are not specifying the direction of the input, when you are not specifying the duration of the hazard, that's only called a potential hazard. But once you go into looking at the circuit and coming up with the gate delays and coming up with the Carnot map delays and deciding that you have a 0 to 1 or 1 to 0 hazard and the duration of the hazard and when it happens and all that, that's called the logical hazard. If I only go with ones and zeros on the Carnot map and I only go looking at gaps between two adjacent ones, all I can tell is that I have a potential hazard. Okay? Whether that hazard happens with the variable, well, the variable that is changing is between these two ones that are adjacent and not mapped, this thing here. The variable that is changing is b, that is going from 1 to 0 or 0 to 1. Okay? All I can say by looking at this is there is a potential hazard. Okay? This is called a potential one hazard. And this is called a static hazard. Static hazard means only one input is changing and there is a possibility of getting a glitch. Okay? Potential static one hazard means that there is a possibility that by changing one input, you get, by changing only one input, you get a zero glitch. Okay? But then you can also have dynamic hazards, which we are not discussing. That is due to changes of input, more than one input. You also have zero hazards, which is this, which means the output has to stay zero, but then there is a one glitch that happens for AND OR circuits. This happens for AND OR circuits. This happens for OR AND circuits. Okay, means the first layer is several ORs, and then the ORs are being ANDed together. This, the left-hand side, or the one hazard, is for sum of product forms. The right-hand side is for product of sum forms. And we are not dealing with dynamic hazards. We are only talking about one input changing, and that one input changing is the changing from 0 to 1 or 1 to 0. But then we have logical hazards. Logical hazards are potential hazards that really happen. Okay? So because potential hazard says, well, if the delay is this, if the delay is this, you don't know about the delays, you don't know about the direction of the input changing or this and that. All you are saying is something is fishy. That means potential hazard. Logical hazard means, well, something is fishy, but that something fishy is really happening. And then you are saying, my input changes from 1 to 0, that happens. The duration is 5 nanoseconds, it happens. And then, let's say 10 nanoseconds after the input changes, the hazard begins. So all these properties, that means the transition of the input, the time after the input change that hazard begins, and the duration of the hazard, all of these decide the logical hazard. I still have one more thing, and that is electrical hazard. If my hazard is so short that the output gate delay is more than that, then that logical hazard that I have decided is going to happen because of the RC delay in the output OR gate is going to be absorbed in the output OR gate. Okay? So I have potential hazards directly. We can get them from the Carnot map. Then you have logical hazards. Logical hazards, you can get them from the Carnot map, and then you can annotate the Carnot map with the gate delays. and you can look at the transitions and come up with the logical hazard. And then electrical hazard. Electrical hazard, you only look at the duration of the hazard and look at the output gate delay. If the duration is less than the output gate delay, that's not going to happen.